All right, let's talk through some of the information necessary in order to complete Lab 4. So in this lab, it's called Falling Objects. You would drop several objects from a predetermined height and then actually use that to work backwards and calculate what gravity seems like it should be. And then we can actually use that to take a step further and estimate what we think the mass of the planet Earth should be. And it all works relatively well. A couple of important formulas we need to know. So in this first one, we need to know that gravity, little g here, is talking about the acceleration that comes from being close to the planet Earth. Then the delta y here is because we're allowing something to fall. It's moving vertically. It's going to use the y component. If we think about how a graph looks and the y-axis is up and down, and technically dropping is coming down, but we just want to know the magnitude or change overall. Then we've got t squared at the end. That's, I think, fairly self-explanatory. Whatever time it takes to fall, we need to square that and use it for a value. This formula relates to several different things. So originally, we had this formula on one of our previous formula sheets and a slightly different format. So a lot of times you'll find this solve for delta y first, so the amount that something will fall. If it's just allowed to drop, then we can simplify the longer formula a little bit, and we get 1/2 at squared. Now you may notice that that's not a perfect match to what's here, but it's not too bad to go back and fix it. To get rid of the 1/2, we can double that fraction, and then to move the t squared away and get a rearranged, we would just divide. So real quick, we can say by multiplying 2 and dividing t squared that we get 2 delta y over t squared. Then, as we talked about before, gravity is a special type of acceleration, so that actually allows us to just substitute in for this formula. The acceleration from gravity will come from 2 times delta y, meaning 2 times the distance something has fallen, divided by time squared, which is the square of the time that it took to fall. These units are good because if we think about how they work out for gravity, on Earth we're used to saying 9.8 meters per second squared, but top part, if it's measured in meters, and bottom part measured out in seconds squared, means that the units line up with what we expect. Okay, then this bottom formula is also related to gravity. So we can see the little g that's in here. Little g and big G are different things from each other, but they are related because we can set them in a formula with each other. In fact, a slight modification of another formula we've used before. We've got little g is equal to big G times big M over R squared. Now, to talk about what these different things are, little g is still the gravity, the acceleration from the Earth. Big G is a universal constant. So that's something that you can look up in a table on a formula sheet, find in a book. Big M in this case is the mass of the Earth. So usually there's a large M because it's a very large object that you're dealing with. And then R squared is the radius of the large object, or separation distance from the center of the large object, technically. But in the case of the Earth, it's the radius of the Earth because we're standing on the surface of it. Okay, then to rearrange between these formulas, if we wanted to get M by itself, then there's a couple of different ways that you can look at this. Sometimes it helps to think about it kind of like a proportion. We stick this over 1 and start to cross multiply. So you'll see that R is being divided on the bottom here, so we'd multiply by R squared. So notice in the formula we've got G times R squared. And then the big G is going to have to move. It's being multiplied, so division would be our way to take care of that. There's a few different ways that you can show this. So sometimes people will, instead of using your proportion, will just multiply R squared over G. And then what happens is that's going to cancel from these. And then that's going to tell us that M is G times R squared over big G. Anyway, that's the connections between their formulas and the things that they stand for. And we can use those to perform the operations that I mentioned for the lab. Okay, so scrolling down a bit. In a full setup, we would run 5 separate trials for one mass and 5 separate trials for a different mass, and then see how gravity compares. Now, in a perfect world, if we were all perfect robots with, mechanized timers and detectors and things, then the time of flight, the amount of time it takes for something to drop, in theory, should be the same for anything that's dropping from the same height. So they can be different masses, they should drop and be the same time as long as they're dropping from the same spot. But because we are humans and it's deceptively difficult to start and stop the timer properly, and reaction time slows things down and so on, as it turns out, is very difficult and would be very suspicious if a student had all the same times in all the different trials. Okay, but I do want to run through an example of what some of this would look like. This is very easy to do. You can drop something from a height. If you have to, you can measure it in inches and convert to centimeters. 1 inch is 2.54 centimeters, and then that would allow you to follow through a similar process. So I've just made up an example. Let's say that a student is dropping something from 91.23 centimeters. Then because of the formula, we need 2 delta y, and we specifically need that in meters so that we're finding the right units for gravity. Then we're going to have a couple of steps to get through. So first, this is asking us to convert between centimeters and meters. So from here to here, that conversion is going to have us divide by 100. So 0.9123 meters. And then because of the formula, clearing out the 1/2 from earlier through the algebra made us double delta y. And so we need to actually do that step now. We want to multiply it by 2, basically just double this up. And that's going to give us 1.8246. Okay, and then let's say that this object took 0.47 seconds to fall. So a little less than half a second to fall this height and then hit the ground. If we're going to take and square that up, so just taking this and multiplying it by itself, then that's going to give us 0.2209, and then when seconds get squared, they just turn into seconds squared. So I want you to recall from the formula that gravity was 2 delta y over t squared. So we found 2 delta y, we found t squared, that's what these columns are for. And we can just plug in and divide those. Because of the way I'm zoomed in, I've got enough room to make it fit, but if you were doing this on your own, you would only necessarily need to write gravity in the block. But if I take gravity is equal to 1.8246 meters divided by 0.2209 seconds squared, then that's going to tell me that gravity is approximately 8.26 meters per second squared. And you might be relieved to know that significant digits are not going to be a huge deal in this one, because there's so many different numbers of significant digits you might get. Some timers have more places, some measurements are to different values. That's going to be really hard to consistently track for students. So we just want to find a value. Okay, but for this one, we got something reasonably close to 9.8. So, at least it looks like it kind of worked. After this, you would follow through and do multiple trials. You would get an average value for gravity in quotes, because again, it's what we think gravity should be. And we want to find a percent error. So in a percent error, we've done this a few different times in different labs before. One of the main things you want to think about that you can use to sort of brute force remember how this works is whatever number you trust to be correct is going to show up twice in your formula. So Earth gravity is pretty well known and understood, and it's been measured lots and lots of times by people doing, better experiments than we're doing here. And so we trust that 9.8, I'm sorry, your textbook I think uses 9.8, not 9.81. But 9.8 is a number that's pretty well trusted. And so that's going to show up here twice. We're going to subtract away the number that we're checking. So the number that we don't necessarily trust is only going to show up once. Now, technically, we have all the units plugged in here, but when we subtract, we get meters per second squared from the difference, and then we divide by meters per second squared. Those are going to cancel away. So all we're really going to end up with at the end is just the percent. Okay, so running through and finding the difference, this is going to give us about 1.54. Then remember it's technically meters per second squared, an absolute value if necessary, but this is already positive. Then the gravity we trust is 9.8 meters per second squared. There's still a times 100 and a percent that we want to remember at the end. Like I said before, the meters per second squared from these will cancel. So again, that shows we're just going to get percent from this. Then finishing this through, we're going to get very roughly about 15.8%, which is not too bad. I've had some groups in the past end up with hundreds, and other groups have ended up with 1 or 2%. So there's just kind of a range. Some of it depends on how lucky you end up getting. Okay, so that process would be repeated for another object, 100 grams. In theory, gravity should be pretty much the same. Well, in theory, it should be perfect. In practice, we don't want to be too far off, but sometimes different people run in the timer, different lucks for how things draw. I don't know. We end up with some kind of random numbers sometimes. In the end, you'd find the average of your averages and the average of your percent. And then one final question at the end. All right, let's go ahead and take a look at this final question. So we want to use your average value, basically that puts all of your 10 trials together, and use that to try to calculate the mass of the Earth. So from the formula we had earlier, we can get the mass of the Earth from whatever we think gravity is, multiplying by the actual radius of the Earth squared, and then dividing by the gravitational constant. From our example here, we would have a gravity of 8.26, and because these are acceleration units, it's meters per second squared. Then that's going to multiply by the actual radius of the Earth. So according to Google, that's 6.38 times 10 to the 6. Then don't forget that in this equation, that's going to get squared. Then all of that is over the gravitational constant. So 6.67 times 10 to the negative 11. The units on this constant are really ugly because they're meant to cancel a bunch of other things. So we have newtons times meters squared over kilograms squared. Okay, so what's going to happen with the units? Some of this is easy to see and some of it's not. So the meters squared cancel the meters that get squared from here. Then we want to remember that newtons are kilograms times meters per second squared. So what that's going to do, it's going to cancel out the meters per second squared from the top. And then these kilograms will cancel the exponent from here. And then kilograms, because they're on the bottom of a fraction, in the bottom of a fraction are going to do this like flip and multiply thing and come up to the top. So you don't necessarily have to be able to follow the units from that because everything's in our standard meters and seconds and kilograms. It's all guaranteed to eventually work out. What we do need to be able to do from this is to calculate through and to find an answer. Okay, so you can take some shortcuts here if you want to use this for later. It'd be helpful on the quiz or potentially on the exam, or if this shows up on the final exam because they're random. I don't know what you're going to see necessarily. You can take the radius of the Earth and square it first, then divide by this constant and basically make your own new constant. And if you have that number, then all you need to do is just multiply by your particular gravity number, and you can find the mass very quickly. That's entirely unnecessary, though, and maybe more effort than you want to put in. So, take that advice as far as you want to. If we calculate this out, we get something like 5.04 times 10 to the 24. so roughly 5 trillion kilograms. The Earth is roughly about 6 trillion kilograms, so this isn't very far off. It's not necessary to do here, but if you did decide to calculate, then this is approximately about 15.7% off. So give or take some rounding errors and slight discrepancies in radius of the Earth and a few other things. Remember from earlier we had 15.8%, so we can tell that this is roughly consistent with our previous calculations.